Welcome everyone to this week's RISC seminar. I'm Lisa Goldberg, co-director of CEDAR, and today I'm delighted to announce our speaker, Vira Semenova from our own UC Berkeley, talking about a subject in causal inference. The title of her talk is Better Rebounds. Vira, over to you.
Yes, thank you very much for inviting me. It is a great pleasure to speak at the RISC seminar. So the title of the talk refers to rebounds, where rebounds refer to the seminal paper by David Lee, 2009, on training, selection, and wages. And I will talk today how to improve them to make them more credible and informative. So sample selection is a central problem in a causal inference. It occurs when a treatment D simultaneously affects not only the outcome of interest, the effect that we are ultimately after, but also our ability to observe the outcome. For example, wages are observed only if a person is employed, and treatment can affect both wages and employment. If we allow the treatment effect to differ across individuals, which means we live in the heterogeneous treatment effect model, the average treatment effect is not point identified. In particular, it means there are multiple values of the treatment effect that the data is consistent with. And the best thing we can do is to do worst best case analysis to bound this parameter from above and below. If we have baseline or pretreatment information summarized by covariate vector X, we can define multiple worst best case bounds. Any subvector of this information maps to a valid pair of population bounds, X prime. And if we're using all information or the full covariate vector X, we can get the sharp or the tightest possible pair of the bounds. So if we had infinite data, we would obviously want to focus on the sharp bounds because they are most informative. But there are trade-offs here, because focusing on the sharp bounds means estimating more complex functions of the data, and we may not have enough sample variation to do that. So the talk today will be about how to use machine learning methods to actually estimate the tightest possible pair of the bounds. Let me make a brief overview of the original identification strategy, how these bounds are constructed. The main assumption behind the bounds is that treatment affects everyone's employment in the same way. So here S1 and S0 are potential employment outcomes in the treated, which is S1, or untreated, which is S0 status. Monotonicity says that if a subject is employed when untreated, that same subject must be employed when treated. So if S0 is equal to 1, it must be the case that S1 is also equal to 1. Originally, this assumption comes from non-compliance literature, where it's postulated on the relationship how the treatment exposure affects treatment take-up. So if I offer someone a treatment, it should be the case that it's easier for the person to get the treatment. But eventually it spread to the selection problem. So it's been imposed on this selection indicators S1 and S0. And sometimes it's hard to motivate because it's unclear why the treatment program should boost everyone's employment, even if it is designed to do so. So this is the main assumption behind rebounds. And the issue in applied work is that this assumption is often imposed without much verification or much attention to it. We will see today in the paper that this assumption actually fails in one of the historical examples. The second issue in the applied work is that the sharp bounds, the most informative bounds, are difficult to compute. And as a result, researchers resort to non-sharp ones. but the non-sharp ones are not informative enough. And in particular, the upper bound can be positive, the lower bound can be negative, and the direction of the treatment effect remains unclear. So it's unclear if treatment helps or hurts on average on the population. So the proposal in this paper is to improve rebounds by making them credible and informative. The credible part refers to the relaxation of monotonicity assumption. Specifically, I require monotonicity to hold only conditional and covariate X. For example, if X contains gender only, then I still require the same direction of selection response for males and the same direction of the response for females, but the directions can now differ across two genders. While previously it was required that the direction is the same for everyone in population, regardless of their observed pretreatment characteristics. We will see that this will actually matter for Job Corps training program to allow for this relaxation. The second contribution is to provide an automated procedure based on modern regularized techniques to estimate the sharp or the tightest possible population parameter. It will be important to distinguish between the concepts of sharpness and tightness. Sharpness refers to the best parameter in population, while tightness refers to the bounds that you actually obtain in your sample and whether they answer the question, the practical question if you want. So my bounds will be asymptotically sharp in the sense that as sample size increases, they will get closer to the tightest possible pair. But of course, they will be not sharp in sample. It's a very hard property. My point is that it is still good for the practical purpose. They will be tight enough. In particular, they will have the same sign and establish the direction of treatment effect. So I will now explain the contributions and there will be a slide for questions. So the first contribution here is the proposal to focus on the sharp pair of bounds. Sharp pair of bounds will mean more complex underlying functions to estimate. I will explain how we can use modern regularized or machine learning techniques to estimate those and produce bounds that are asymptotically valid. I will extend the Lee bounds to handle various practical difficulties. So often in practice, we have non-compliance in randomized trials, which means even if the treatment is offered to a person, it's actually not accepted by the person it's offered. And the acceptance decision is endogenous, it's based on the expectation of the outcome. So this issue of non-compliance is typically handled by a parameter called local average treatment effect. And I show how we can bound this parameter if we have selection problem. The third part here refers to quasi-experiments. Quasi-experiment is a situation where we have a lottery, but we cannot perfectly manipulate how subjects get into treatment and control group, or there could be multiple types of various groups, which means we end up not knowing the probability of treatment assignment, the final one. Original Lee bounds assume that you know this probability. So my proposal is to extend the Lee bounds to handle unknown probability of treatment receipt. The empirical findings here are first, that monotonicity fails in Job Corps training program. This is one of the federally funded training program that helps youth to gain more human capital and through various forms of training. I show that this program actually hurts someone's employment chances in contrast to what was believed before. Second, I show that the worst and best case bounds are almost identical in the two empirically important contexts, the Job Corps one, and the other one is the Oregon Health Insurance Experiment, whose main purpose was to study the effectiveness of Medicaid on low-income population. Okay, so I will describe the literature as it goes. I would like now to pause for questions. Are there any questions? Okay.
We're
So,
good for the moment.
Yeah. Okay. Okay. So now let me start by giving a brief overview of rebounds. To start with rebounds, I need to introduce potential outcomes notation. I will do though in the context of training and wages. So if D is equal to 1, if subject wins a lottery to get assigned to a treatment group, and D is equal to 0 if the subject remains in the control group. S1 and S0 are potential employment outcomes for when the subject is treated or not treated. And likewise, Y1 and Y0 are potential wages when subject is treated or not treated. Of course, we never observe the potential outcomes, we observe only the realized ones. This notation here, Y is equal to D times Y1 plus 1 minus D times Y0 shows the connection between the actual wage and potential wages. The actual wage is equal to the potential wage Y1 if the subject is treated, and potential wage Y0 if the subject is not treated. The main issue here is that this realized wage exists only if the realized employment, which is defined in the same way, is equal to 1. Potentially, treatment can affect both S and Y. So comparing the treated wages and untreated wages will contain the effect on wages plus effect on employment that we're trying to get rid of. Now, the target population that I'm going to focus on is what's called the always takers. This is a partially latent group of people that are employed regardless of receiving treatment. In particular, their potential employment at status 0 is equal to 1, and potential employment when they are treated, that is also 1. Of course, we don't know who the always takers are because we observe only one of the two potential outcomes. And the parameter of interest is the average treatment effect. So the treatment effect for a person I is the difference between their wages when treated and untreated. My goal is to focus on the average parameter that is conditional on being on the always taker. You may ask why the always takers is the population of interest. And it's of course a very fair question. It is mostly based on convenience because for this group of people, we observe the most data. So the bounds will be the most informative. Generally speaking, why the always takers are more interesting than other groups is a subject of a separate question, separate study. So this is the setup of lead bounds. Here's the main idea. Because we need to bound the average treatment effect, we should talk about the expected wage when treated and expected wage when untreated. So it turns out that expected wage when untreated is actually point identified, meaning there is only one unique value in population that is supported by the data. To see why this is the case, let us look at the untreated wages. Because the untreated wages belong to the people who are unemployed in the untreated status, all of these people must be the always takers. So if a person is employed when untreated, S0 means 1. By monotonicity, S1 is also 1. So these people must be always takers. And therefore, by random assignment of the treatment, this is a random sample of the always takers. So we know what's the expected potential wage in the absence of treatment is. Now, in contrast to this group, the expected Y1 is not identified in the sense there are multiple values of this parameter that are consistent with the observed data. Reason for this is that the treated wages is actually a mixture of two types of the people. The always takers group that we have just seen, and another group that have been induced into employment by the fact of receiving treatment. This additional group can be substantially different from the target always takers group. And therefore, we want to separate it to understand what's the expected wage of the always takers, so that we compare always takers in the treated and in the untreated group. Fortunately, as Lee has observed, we know what the fraction of the always takers' wages is. And this fraction is equal to the employment ratio. The main point here is that this is just a known thing in population, and we can estimate it by computing the employment ratios in the untreated to the treated group. And it's always in between 0 and 1 by monotonicity assumption. So once this is done, the remainder part is actually worst best case analysis. So if we focus on the left plot here, we will see the distribution of the treated wages that is shown by the histogram. The vertical blue line shows the quantile of the level P0 of the treated wages. So here on the plot, P0 is around 0.8, and the quantile of this distribution of level 0.8 is around 2.4. So in the worst case, the always takers are all behind this additional group, and they are shown in blue. They are all below this vertical threshold. This case corresponds to the lowest possible value of the expected Y1. If we focus on a symmetric case, we will develop a threshold at the level 1 minus P0, which will correspond to the always takers being at the top P0 quantile of this distribution. And we will get the largest possible value of expected Y1. So this is the whole idea of the Lee bounds, how David Lee proposed this. There are two fortunate aspects of this idea in connection to the standard setting where we have only one possible value of parameter. First, if P0 is actually 1, so if P0, if the employment ratios are equal in the treated and in the control group, that means the treatment does not matter for employment at all. And we can compare treated and control wages just in a standard way. The Lee bound nests this case because when P0 is equal to 1, the quantile will be at the at the level 4 on the left panel. So the whole mass will be blue on the left and on the right panel, and the bounds will collapse into a point. So the worst case bound and the best case bound will be exactly the same. Likewise, now imagine so that P0 is not 1, so treatment actually does matter for employment. But for some reason, the wages are very concentrated, so they look like a point mass. This is another very fortunate case because if they look like a point mass, it doesn't matter which quantile you're considering, and the bounds will collapse into a point naturally. The second property is something that I'm going to exploit going forward, because as I reveal more and more additional information in the form of baseline covariates, I'm reducing the spread of the wages conditional on covariates, and I'm making the bound tighter. So that's my plan in terms of tightening the bound by including additional information and reducing ambiguity between the worst and the best case. So any questions up to this point? Okay, so I will now describe what the better Lee bound means in the one-dimensional case first. So better Lee bound, so my proposal of the bound, actually focus on the same population parameter as the original David Lee paper, but changes the way how this parameter is estimated. So the least sharp upper bound here, written here, looks like an integral of two functions, where the first one is the covariate specific upper bound, beta ux. And this part is, of course, estimated on the treated group, just like we have seen the plots before. but it's integrated against the covariant distribution among the control wages, which is written by the function fx given s equal to 1 and d equal to 0. So to compute the bound, we actually need to use two samples, the treated sample for beta u and the control sample for the density, which makes a lot of difficulty now because this integral does not look like an expectation. And therefore, if we now map it to the sample, if we now need to estimate this parameter using a finite sample, we will need to discretize our covariates into a small number of cells so that within each cell, we can have treatment control difference to compute the bound, and we can actually compute the probability mass function of each cell. So this bound can be defined only if X, the covariate vector, has only few covariates, for example, gender or race categories, something that is coarse enough so that within each cell you have variation in treatment control wages. Once you consider, for example, age, you now need to discretize age because for certain values of age, you may not have this probability function estimated sufficiently well. This is the main hurdle towards getting the sharp bound because you cannot exploit your covariates in the full information you have. So the main trick to get rid of this hurdle is actually to use the Bayes rule. Bayes rule allows us to replace the covariate density, which is written here as fx, by the probability of selection. If we work on this vertical line here, the Bayes rule line, we can exchange the order of the selection indicator as equal to 1 with the covariate vector x. This is very important because now we obtain this unconditional covariate density fx that will bring this expression for the bound and make it look like an expectation. Expectations are much easier to handle, and in particular, this conditional probability of selection given the treatment is also easy to handle because covariates are now on the right-hand side of this vertical bar. This is a conditional expectation. This looks like a classification problem. We can use regularized methods to estimate it. Whereas before, there is not that much methods to estimate the density, and with high dimensional covariate, this becomes harder to do. So Bayes rule allows us to remove the density and introduce functions that we can estimate based on regularized methods. So after some additional steps, I arrive at the moment expression, so this expectation for the bound itself. I do obtain certain first stage functions that look like probability of being employed conditional on covariates, various conditional quantiles of treated wages, as shown by y(u)x, and the probability of treatment assignment, or the propensity score. So the best part here is that all these functions contains x's on the right of the conditioning bar. So they look like a conditional expectation or conditional quantile. We have methods to estimate them, but for example, by importing regularized techniques for classification or regression from machine learning. If we suppose that x is actually lower dimensional, and we don't need these techniques, we can already use this expectation to compute the bound using the methods described above. But to use regularized techniques, we need to make an additional change. So here is the reason why directly using regularized techniques is not going to work. Suppose now we have a selection equation S0x that we would like to approximate by a logistic function of x prime gamma naught, where x is our covariates and gamma is the parameter that we're using to parameterize. In the first stage, I would like to estimate gamma by a regularized technique, for example, logistic lasso. And lasso is going to throw away some covariates by construction. Some covariates that are very important will be selected by lasso. but some that are moderately important, but still not zero, they will be zero out, and they will become part of the error term. So they will be not included into the estimation of the selection equation. Once they become part of the error term, this error term is now correlated with the true object, the expression for the bound. And this correlation is like an omitted variable bias type of correlation. It biases the parameter, the distribution of the parameter relative to the truth. So this picture illustrates this issue of the bias. And the blue curve shows the distribution of the moment equation, assuming that gamma naught is actually known. So it looks like the distribution of sample average, and it's correctly centered. It has all the desired properties, but the blue curve is not feasible to us because we don't know gamma. So we would like this histogram, which is the distribution of the feasible estimator, to be close to the blue curve, but bias is preventing us from getting it. So the discussion will follow then what we can do about this moment equation so that these two plots are actually the same. The idea that presented here is called orthogonality. The idea is to adjust the definition of the bound to ensure that it is not sensitive to the bias, so that eventually the two plots will become the same. Please know that the first stage has remained the same, and I will be making changes only to the second stage, replacing the moment equation mu by gu. So here is now how to conduct this replacement. The idea of orthogonality have been introduced broadly by Niemann and connected to machine learning by Chernozhukov and Whitney Nguyen. This is an application of this idea to the least problem. So the first step is to write a Taylor expansion of the moment equation for the bound around the parameterization of the selection equation gamma naught that will produce the derivative of this expectation with respect to gamma. When I go ahead and compute the derivative, it turns out that this derivative is not equal to zero. And this is the whole reason why the regularization bias in gamma translates into the second stage. This channel of this translation is the derivative, and the derivative is not zero. The idea proposed by Whitney Nguyen in his 94 paper is to come up with a random variable called bias correction that has two properties. First, this correction does not change the location of the moment. So in expectation, it must be equal to zero. You're adding a mean zero term that will not change the location of your bound. If you look at the expression for the correction, you will see that by law of iterated expectations, it is equal to zero, because it is a product of some residual that is mean zero conditional on covariates times the function, something that is a function of the covariates only. So by law of iterated expectations, the correction is valid. Now, the purpose of the correction is to actually kill this bias problem. When you add this correction to the original moment equation, mu, the final moment equation gu will become orthogonal to the parameterization gamma, in the sense that the derivative of this expectation with respect to the parameterization will now become zero. As a result, this regularization bias in the Lasso estimate will have no first order effect on the bound itself. If we assume that all other higher order terms do not matter because gamma converges sufficiently fast, then it will ensure that the feasible estimator based on Lasso will have approximately the same distribution as the infeasible estimator that is based on the truth and therefore unattainable. Are there any questions on orthogonality or yeah, broadly speaking about what's there, how this comes up? Okay. So there will be a moment for questions later on as well. So here's the proposal for the Berkeley bounds. The Berkeley bounds have 3 steps. The first step is to estimate this first stage parameter gamma by a lasso, logistic lasso, and the quantile function by the quantile version of the lasso, where the penalty choices are fully automated and proposed in the work by Beloni, Chernozhukov, and co-authors. The second step would be to compute the preliminary bound that is based on the orthogonalized moment equations, GL and GU. Now, the little issue is that because you're adding the mean zero correction to the lower and the upper bound, the bounds can now actually cross. And in particular, the estimate of the upper bound can now be smaller than the estimate of the lower bound. So if the true parameter is, say, true ideal bound has -1 and 1, beta hat U can actually become something like minus a negative number, and beta hat L becomes a positive number. So the bounds become nonsensical. But it turns out that if you sort the bounds, so if you impose a logical shape restriction that they must obey, these bounds can only improve in terms of their statistical properties. So sorting is fine. It may look like you are doing something to fix a problem, but you are actually improving their statistical properties by doing that. So if you have a negative upper bound and a positive lower bound, you should just sort them for the purpose of estimation. Okay. Questions? So this is a theorem that shows why the bounds are suitable for estimation and inference. It says that if the sparsity indices of the selection equation and the wage equation are sufficiently small, then the preliminary bounds are jointly normal. And the asymptotic covariance matrix of these 2 bounds is known. The particular useful feature of this theorem is that this asymptotic variance matrix depends only on the second stage orthogonal moment. Imagine typically that you have a 2-stage procedure, like 2-stage least squares in econometrics. We know that manually computing the standard errors for this parameter is not going to work because of the 2-stage structure of the method. We need to account the uncertainty that comes not only from the second stage, but also from the first stage. And therefore, it's important to use the pre-programmed software to do this. Here, the issue is resolved by focusing on orthogonal procedure, where the asymptotic variance is fully determined by the second stage, and there is no uncertainty contribution coming from the first stage whatsoever. So this method is coded in the Rebounds R package on GitHub, and you're welcome to try it. Okay, so let me see how much. Okay, so now I will discuss about robustness checks. So the main assumption behind the first method that I've just described was the sparsity. Indeed, to use lasso, we need to ensure that the original parameterization is sparse, or effectively it means that there are few covariates that affect employment or wages. But these assumptions may not be always economically plausible, which will result in the bounds with poor properties. The method described here does not require sparsity, but at the same time does not guarantee sharpness. It is based on the work by Chernozhukov, Esther Duflo, Ivan Fernandez-Val, and Demir, and it adopts the ideas from heterogeneous treatment effect literature to the literature on bounds. So the first proposal here is to split the sample into 2 halves. The first half will act as an auxiliary sample, and the second one will act as the main sample. The auxiliary part will be used to choose which pair of bounds you want to compute. And the second one will be used for estimation in a standard way, just the way I described so far. So you can think about the method described so far applicable only for the second bullet point. And on the first one, I will be actually selecting covariates. So we can use arbitrary regularized technique to do so. For example, random forest, when you regress wages on outcome using random forest, it will produce a ranking of the features based on their predictive power. You can use this ranking to determine top 10 or top 15 covariates, and then focus on the bounds conditional on those covariates. Because they're using the different samples for selection of the parameter and for estimation, this is statistically valid procedure. And the coverage of the parameter will be asymptotically correct. However, a slightly unappealing feature of this method is that you can split sample into two halves in an arbitrary way. And depending on how you split, you get a different number. So this is not good for communication purposes. So variational approach acts like an additional layer where you generate multiple splits. You repeat the conditional part, and then you report the median of the lower and the upper bound. This median stabilizes the estimation, but the cost of this is the slight inflation of the coverage rate. So in addition, instead of having 1 minus tau coverage, you'll have 1 minus 2 tau coverage, where tau was the coverage of the original confidence interval within one split. So this is as proposal for the robustness check to the main analysis conducted on the full sample under the sparsity assumption. So the final slide here for this theory is about relaxing conditional monotonicity. In the Lee's paper, monotonicity was required for all subjects to hold, and I would like to relax this assumption by requiring it to hold only conditional on covariates and allow the direction of the selection response to be different based on observed characteristics. So the way Lee handled that is he proposed to compare the employment rates in the treated and the control group and take the ratio of P0. If the treated group is doing worse relative to the control, if the control group is doing worse relative to the treated one, then it means that treatment actually helps employment. So if the estimate of P0 is less than 1, we have a positive selection response. Otherwise, we have the inequality in an opposite direction. The relaxation here is to split the covariate space into two halves, estimate the boundary of the covariate space, and then classify subjects into the one part or the other. Unfortunately, as of today, this requires the uniform convergence of the estimated function to the truth, which can be viewed as a strong assumption. We have this uniform rates only for Lasso at the moment. So I plan to relax this to accommodate incorrect classification based on the work shown on the slide. Okay, so the main takeaway for the Berkeley bounds is that they are moment-based. They're based on expectation as opposed to the density. Basing the bound on expectation has many advantages. First, they can accommodate not only discrete, but also continuous covariates, and not only a small number, but also large. They can import existing results on how to use machine learning and regularized techniques using orthogonality idea. And as a result, they're tighter in practice. The density-based bound, in contrast, accommodate only few discrete covariates because they require the density estimate to exist. They are sharp in the finite sample, but they are unlikely to be tight because they cannot handle sharp population bounds with many covariates. So at this moment, yeah, I would like to pause. Questions? Okay, so I will then talk about empirical findings. Then I will, if time permits, I will talk about theory. So the first empirical finding concerns the Job Corps training program. Job Corps is a federally funded training program that helps young individuals to get a better job make more money, and gain control over their lives. It operates by having multiple centers in many US states, where an individual arrives to the center, has a counselor and chooses the best course of training, be it to complete an uncompleted high school education, get vocational training, get psychological counseling. So there is various kinds of services you can do in Job Corps. The average time of training is around 8 months. Back in 2000s, mathematical policy research conducted a randomized trial to assess the effectiveness of this program on wages. To understand, is it indeed the case that individuals gain more human capital that allows them to make more money by receiving higher hourly wage? The sample I focus in the same as the sample of Lee, but the covariate set, so the observations or the rows of my data set is exactly the same as this Lee, but the columns, I have many more columns or covariates compared to Lee. Lee, in his original work, manually selected only 28 demographic covariates, age, gender, prior work experience, etc. But I plan to use everything that is available in that data set, which amounts to around 5,000 covariates. And the important covariates here include the reasons for joining Job Corps, medical, arrest, and drug use records, as well as wage history 1 year prior to the random assignment. So the baseline or pre-randomization covariates captured information before random assignment is conducted. After random assignment is conducted, we follow up both the treatment and control group, and we record employment and wages for 208 weeks after random assignment. So we have 208 pairs of employment and wages. The goal is to
question.
Yes.
Okay, so I think this is in effect a question about the theory that I didn't understand. So you've got a truly stunning number of covariates here, about half the number of, it's about half n. So normally you would think you couldn't do that. So what's the trick in the methodology, or what's the insight in the methodology that lets you handle such a large number of covariates with 9,000 samples?
Yes, thank you for that question. So the assumption here is that out of these covariates, you can reduce these covariates into a smaller number of those that matter, but you don't know which ones matter. Let's focus on the wage history. Wage history is a record of indicators where the person worked throughout the whole year before random assignment. My assumption here is that the person didn't switch jobs many times. So if you focus only on, say, 10 out of 54 weeks, this will be adequately capturing the whole history. And the residual covariates have zero differential effect relative to those 10. But I asked Lasso to find those 10 moments that matter for the history. If you focus, for example, on medical issue, I assume that each person has few diseases, and therefore I asked Lasso to find binary indicators for the relevant diseases, assuming that there are few diseases. And likewise, that drug use, so one person can only have few. Sorry, I think I'm wrong. I mean, there are few diseases that matter, but we don't know where they are. But the diseases are the same for everyone. It's not like each person can have its own list of few diseases, but these diseases also must be common. So this is a stronger assumption. This effectively means sparsity.
Okay, thank you. That's helpful.
So this sparsity allows us to handle this many covariates, as well as we have this employment and wage data. And the goal now is to measure the effect of treatment or Job Corps assignment on wages. So this figure shows that monotonicity that was previously assumed to exist actually fails. On the x-axis, we have weeks after random assignment. And on the y-axis, I have difference in employment rates between treatment and control group. So if we focus on just 1 week, for example, week 40, we will see two circles, the black and the gray circle, that are designed so that the total number of people in these two circles is equal to the sample size. So it's around 9,000 people. The subject in the black circle correspond to the people whose predictive effect on employment is positive. So subject in the black circle are actually better off because they assigned for the job corps. This helped their employment chances. While the subjects in the gray circle, they were harmed by, in terms of employment, by signing up for the job corps. The size of the circle is proportional to the number of people it contains. So we see that across time, people move from the gray to the black circle. So this picture can be roughly divided into 3 time periods. From the week 0 to 40, almost everyone is hurt by job corps, which makes a lot of sense because if you go to the job corps, you cannot hold any other kind of employment by the nature of the full-time commitment. So job corp mechanically prevents employment by signing people up. And this is true from the week 0 to 40. So monotonicity does hold here in this region, but in the negative direction. Now, if we look at the sometime around week 80 to say week 100, the circles gray and black are roughly of the same size, which means that exactly 1/2 of the population is being helped by treatment, whereas the other half is being hurt. So monotonicity assumption is the worst for this period because there is no direction that will be particularly meaningful. Half of the people are being hurt and half are being helped. There's no reason. The majority vote will be exactly very hard to do here. And in the final part of the plot from the weeks 120 to 200, we see that majority of people are being helped in terms of their employment chances, but there is still an untrivial fraction of subjects who are being permanently hurt by the job corps in terms of their employment. So the previously assumed monotonicity is actually doesn't hold for this data set. Another way to represent the same information is by plotting the fraction of subjects in the black circle, which is shown by this curve here that is increasing. And an alternative piece of evidence against monotonicity is represented by the shaded area. That is a summary of monotonicity test that does not require the logistic approximation that the previous curve does. So it's an alternative piece that that is robust to logistic assumption. The dark gray area shows the weeks where monotonicity is rejected at the p-level 0.1. So this is the strongest evidence. The light gray is the medium strong evidence, and white weeks is where monotonicity cannot be rejected. So we see that even in the final weeks where the data collection period ends, monotonicity is still not restored. Here is another evidence why monotonicity doesn't hold and why imposing monotonicity erroneously creates nonsensical predictions. So this table shows two types of results. The brackets show the estimated upper and the lower bound, and the parentheses show the confidence interval that covers the true parameter with probability 0.95. So of course, confidence interval is often wider than the brackets because brackets are just best guesses of what the bound is, while the interval is something that covers the true parameter with a very high probability. We have 3 time periods and 2 columns. The first column is the Lee's original estimate without any covariates. And the second column is the least density-based estimate based on the 5 discrete covariates. So if you look at the middle week, the week 90, the covariate-based bounds are actually wider than the basic one, in contrast to what theory predicts. Theory says that they should be much tighter. But here we have the opposite direction, and it looks like the theorem doesn't hold. So it turns out that because monotonicity is erroneously imposed, you need to manually truncate your trimming thresholds to ensure that they point in the same direction. If you have 5 discrete groups and 4 of them suggest that monotonicity, the treatment is helping, but one of them suggests that it's hurting, you need to manually change the direction in one of the groups so that they all point in the same direction. Once you make these manual changes, the sharpness theorem no longer holds and the bounds are not guaranteed to be tighter. So this is another reason for why monotonicity is likely to fail. And second, why the bounds are going to get worse if you impose this assumption erroneously. So any questions so far? Okay. So I will then describe how we can use the proposed methods to properly estimate the effect of job corps on wages. This table all shows results under conditional monotonicity, so the weaker assumption. The 6 columns here reflect 6 different choices of the covariates driven by the method. In particular, the numbers 28 and 15 reflect the number of covariates I include into the selection equation, which is the first 2 rows, and into the into the wage equation, which is the 3rd and the 4th row. So the first column here shows the bounds on the estimated effect on wage if I use only the information that Lee selected. And even though these bounds are sharp in that model, they're not tight enough because they are not able to determine if job corps is helping or hurting wages on average. So this is not particularly useful. The column 3 is the column where I use the full set of information set, assuming that there are few covariates that affect wages or employment. So there are few diseases that matter for employment, and there are few, say, drug history records that matter for wage. When I impose this sparsity assumption, out of 5,000 covariates, logistic loss selects only 9 for employment, and quantile loss selects only 6 for the relevant wage quantiles. So the dimension reduction happens in a massive way, and the bounds become very tight. In particular, they now suggest that job corps does improve wages by 4%, between 4 and 4.6%. And this effect is significant because the lower end of the confidence interval is positive. However, column 3 is sensitive to this assumption of sparsity where there are few covariates. So to relax sparsity, I do something in the column 4. In column 4, I take the union of the loss of selected covariates in column 3. So this union consists of 9 plus 6 covariates, 9 employment, 6 wage, minus 0 overlap, which gives me 15. And this is now my target parameter, the bounds conditional on 15 covariates. These bounds come out a little wider and they lose significance, but they no longer assume sparsity because I estimate them, I do not use regularization anymore. The number of covariates I include is the same as the number of covariates that go out into the first stage, so it's 15 everywhere. The reason why I don't stop in column 4 is because the significance here of the confidence interval is actually wrong. It does not reflect the uncertainty with which I selected the bound in column 4. So in a different universe, in column 3, I could have selected different covariates where 9 could come out as 10 and 6 can come out as 7. In that different universe, the column 4 would become 17. So the parameter would change. And the uncertainty that comes here should be reflected in this confidence interval in the column 4, but it does not. The confidence interval assumes that this is the truth, where in fact there is selection behind it. So to have a proper uncertainty quantification, I report column 5 and 6. Column 5 is this robustness check based on the auxiliary sample. In the Lee data, this auxiliary sample naturally exists. So I use the full 9,000 observation sample to compute the bound. And on auxiliary sample, I select covariates using random forest importance ranking. The bounds come out very similar to column 3 and 4, but the confidence interval is slightly wider, accounting for this additional uncertainty of how covariates are selected. And finally, in column 6, I use the variational bounds, which is robust to the choice of the sample of the auxiliary sample selection. The bounds are still wider, but still positive. So the main takeaway here is that Job Corps seems to indeed have a positive effect of wages at week 90 for the people who are always takers at week 90. But this effect may not be significant because significance requires sparsity. Okay, so this was a demonstration for the Job Corps training program. Here is another demonstration for an alternative experiment where the main goal is to show how to handle non-compliance. So in the previous table here, the interpretation of this wage effect of 4% was the effect of being offered Job Corps a spot at the training program. But we don't actually take into account whether the person takes up that spot or not. So these magnitudes are naturally shrunk to 0 because not everyone who is offered admission actually takes that admission. In the next couple of tables, I will show you how to compute bounds on the parameters where this non-compliance is actually handled. So, but the data set will be slightly different. So in 2008, there was an experiment in Oregon where a random set of subjects were offered admission to Medicaid. Pre-randomization covariates include survey waves and household fixed effects, so the number of people in the household. And there was an additional 54 covariates, including pre-existing health conditions, healthcare utilization records, and measures of socioeconomic status in terms of the SNP and TANF enrollment. The notation is going to change slightly. In addition to have D, we also have a variable called Z. Z is what's called an instrument that is equal to 1 if subject wins a lottery and 0 otherwise. D is the subject's decision to sign up for Medicaid. Non-compliance means that Z equal to 1 does not imply D equal to 1. So if a person wins a lottery, it does not mean that the person chooses to go on Medicaid. Likewise, if Z is equal to 0, so if the subject loses a lottery, it does not mean that the person cannot sign up Medicaid through other channels. So this is measuring the effect of this particular experiment. But so it's because Z and D are generally different, we have this non-compliance problem. Y, the outcome Y is the self-reported number of days in good health. So after random assignment is conducted, 6 months after that, subjects are mailed a questionnaire about their health outcomes, and they're asked about various questions of how are they feeling. So Y is the response to that question, and S is an indicator for whether the response is not missing. So we want to know the average effect on the people who would have responded regardless of being offered their Medicaid exposure. So here is the table. It is slightly different from the table we have seen before, in particular because it focuses on the worst case bound only. For this reason, we have just one number in each row as opposed to two. And this number is shown with no additional parentheses. The number in parentheses is the standard error of the estimate. So the purpose is to determine whether the Medicaid has positive effect even after accounting the non-response bias in the survey. The rows of the table indicate the various health outcomes relating to the overall physical and mental health. The columns of the table reflect various types of analysis, where the first group reflects intent to treat, and the second group reflects the local average treatment effect. So intent to treat is the effect of the exposure of Medicaid, while the latter one is the effect of actually going through Medicaid. And if you look at the first three columns, the numbers are closer to zero naturally than the columns 4 through 6. Now, within each panel, we have three types of methods. The first one is what's called as treated analysis, where you assume that the reason why people don't respond to a survey is exogenous to their health outcomes. So you can just focus on the observed responses and ignore non-response bias altogether. This is what's referred to as non-column. So it means no truncation or like no bias at all. Column 2 is the least method, and column 3 is the non-parametric methods combined with the better rebounds. So it's my method. So let's focus on the number of days in physical health. As treated analysis suggests that getting Medicaid should increase the number of days in good physical health by 1.5 days with a standard error of 0.6. So there is indeed at least one better day in physical health attributed to the fact of being on Medicaid, so accepting Medicaid. However, if you start conducting robustness of this to non-response bias, you will lose your result completely because the lower bound is negative. So Lee is not able to tell you whether the effect is positive or negative because the lower bound is negative. And finally, the better Lee bound is positive, but not significant. So it suggests that in the worst case, the Medicaid will attribute to half out of the 1 day in months to your good day in physical health. However, this is not significant, so we don't know if the effect is significant or not. Are there any questions on the second empirical example related to non-compliance? Okay. So these were two demonstrations. I think I have still 15 minutes. So I would like to briefly sketch the main theoretical findings using this plot here. So in addition to the non-compliance we just discussed, another difficulty perceived by the paper on the Oregon health insurance experiment is how to report an aggregate measure of the treatment effect if you have multiple outcomes. So in the previous table, we have seen multiple rows. Suppose we focus on the two rows, the physical and the mental health. You have two estimates, but we need to report one number to a policymaker to make further decisions. Two numbers is too much information. You need only one. So the way typically people aggregate this is using standardized treatment effect, where called STE, that is defined as the sample average of the treatment effect for the physical health plus the mental health divided by the standard deviation of the respective outcome in the control group, as shown by zetas. The main difficulty here is that this normalization constant zeta1 and zeta2 are unknown, and you need to estimate them. So I extend the Lie bounds to handle this complication, as shown on this graph. So this blue circle is the identified set, so the pair of all possible outcomes for the effect on physical and mental health. This gray line is the true, correct line on which you should project this identified set to get the upper and the lower bound on the standardized treatment effect. In this case, if the standard deviations of the two outcomes are the same, this projection line is 45-degree line. So you just need to focus on the projection on this, on the point where the line intersects the set. But the problem is that you don't know where this line is. This is a population parameter, the direction of this line. You need to estimate it. And therefore, you need to have a good estimator that has good statistical properties, not only at the point of the intersection as shown by this black dot, but also around the neighborhood, so that the estimate is approximately normal, not just at one point, but approximated by Gaussian process in the neighborhood. So this is also now possible by the Lie bound for the standardized treatment effect and implemented in the package. So I will then go to my conclusion slide. So the main summary of the better Lie bounds is that they are better in the two respects. They are robust to monotonicity violations, and they allow differential response, different response direction depending on observed characteristics. And they are also tighter. So the gap between the worst and the best cases is smaller. They are asymptotically sharp under two assumptions. Either if we have a smooth model with few covariates, or if we have a lot of covariates, like in the Job Corps program, but there are few of them whose identities we don't know that matter for employment and wage. And finally, the Lie bounds accommodate a non-propensity score, non-compliance, and multiple outcomes. So thank you very much for your attention.
I have an elementary question. I apologize. It picks up on Bob's question, which is, it seems that you started with a very large number of covariates and then used the lasso to reduce the dimension to a much smaller number of covariates, and then analyzed the statistical relationship based on that much smaller number of covariates. And one would expect that in such a process, you'd lose many degrees of freedom, which would have a negative impact on the confidence, on the power of the tests and the width of the confidence interval. And I'm not sure I fully understood your response. Could you say a little more on that point, please?
Yeah, yes, thank you. So I think it's here, right? Indeed, in column 3, I assume sparsity. So I started with 5,000 and that got reduced to 9 in the employment part. And likewise, in the wage equation, I started with 5,000 that got reduced to 6. So the comment here is because I'm using, Lasso has selected very few covariates. As a result of that, the confidence interval should be wide because I lost covariates. Is that the question?
That's helpful, thank you.
No, sorry, I'm saying that if the true model is sparse, because you have Lasso has zeroed out something that is truly 0 and something that is close to 0 but not 0, you actually improving the efficiency because you have more sample size per covariate. So if n over d minus, your standard errors in the denominator have something like n minus k, where k is number of covariates and n is the sample size, because the smaller the K, the smaller the standard error. So this is actually good, but this can only work if the true model is sparse. So that's the assumption that we cannot test. It's underlined column 3.
Thank you.
So let me follow up on that. So if I understand what you said, it sounds as if the following is true. If all, or let's say half of the covariates matter, but none of them have a big effect, lasso might well get you down to a small number of covariates. But if the true model were not really sparse, then you've got omitted variables problems, a variety of other things. So that's really what you're relying on, the assumption that the true model is sparse. Is that correct?
Yes, exactly. And this is the reason why the table doesn't stop at 3, because sparsity is quite a strong assumption for practitioners. So ideally, we should have something like a robustness check in column 5 and 6, where sparsity is not imposed.
So it's almost as though the assumption is that sparsity is ground truth and the lasso accurately finds it. So there's not only no loss of power, there's an increase in power because the sample size per covariate has just gone up.
Yes, that's right. So a small comment on lasso accurately finds. So there is a distinction between what's called perfect model selection, where probability of selecting all true covariates is 1, and imperfect, where it's not 1. The perfect model selection is thought to be a very impossible assumption because it requires the covariate either to have a very large effect or no effect at all, but it rules out existing of this moderate phase. This is not what the bound assume. The bounds do not assume perfect model selection. The orthogonality idea presented earlier is the way to kill perfect model selection, get rid of it, and allow imperfect model selection, which means existing of the moderate zone for the coefficients, where covariate is impacting, on the one hand, it's impacting the selection, but at the same time, it must be zeroed out to ensure convergence. And therefore, because it is zeroed out, it goes to the omitted variable bias. Orthogonality deals with that. So there is a distinction between selecting in perfect or imperfect sense.
Thank you.
So one place I and other people in the audience have used lasso is in conjunction with latent factors. So for example, you're doing PCA, but you impose a lasso constraint in order to get a smaller number of sparse factors that may be more readily identifiable than the ones that come out of PCA. So the sparsity there is that a factor is viewed as being relevant to a selection of in our case, it's stocks. It's used for things like there are, firms that are in a particular industry or firms that are in a particular country, and so a given country or industry factor doesn't affect very many of the stocks. Here you're looking at specific covariates that are given to you, and they're not latent factors. That's correct, right?
Yes.
So okay, so it's a different application for sure. Have you thought about trying to impose sparsity, but in a setting where instead of zeroing out the individual covariates, you're looking for a lower dimensional structure, linear structure within the covariates that explains your data?
Yes, I think this is a good idea. The only caveat is here, if I think about standard PCA, this is an unsupervised problem. So there are no labels that guide on how I construct this low dimensional structure, right?
Right.
So the main reason for why bounds go tighter is how well the covariates explain the outcomes. So if the covariate is super predictive of wage, then conditioning and it should make the bounds collapse. In that sense, having having labels does help to pick which covariates matter. So there is I think a stronger link to supervised methods where you use labeled data than to unsupervised ones like PCA, because you want not a good summary of your covariates, but the covariates that are a good summary of wage or employment.
Okay.
Yes, but I'm working now on a simple model that makes the link to the, say, first stage R squared and the bounds width very clear, so that the prediction link is more obvious. Currently, it's not obvious why Lasso is better or worse than PCA, and all these methods, they look equally good, but if I can establish a direct connection between the first stage R squared and bounds widths, then it should be more compelling to use supervised methods.
Okay. And one last question, if I may, did you think about using other machine learning techniques, for example, random forests, as opposed to Lasso? I'm not saying that's a better method. I'm just curious about whether you thought about that and what led you to choose Lasso as opposed to other alternatives.
Yes. So random forest, Lasso was chosen primarily because first there is this clear underlying the sparsity assumption that it can be linked to. So it's clear what you should impose on the true model so that the convergence, so that the Lasso picks approximately right set of covariates. Whereas for random forest, it's less clear what this assumption should be. And the second part is the automated choice of the tuning parameters. So for method to be sort of acceptable by applied community, it has to be fully automated. And for Lasso, these automated penalty choices do exist. But for other methods like neural network, it becomes a bit more ad hoc and based on cross-validation or some other techniques. So it opens the door to drive your bound to the tightest possible thing, which is not good. And I don't have a good way of protecting from this to happen. For that reason, I focus on Lasso just for sort of transparency reasons. But of course, if there is a good intuition for a researcher why random forest is better, then of course one should use random forest. The paper actually the method is a high-level description. You can use in the first stage whatever you would like, as long as you can prove that it picks the right covariates, and you can come up with automated data-driven penalty choices. Then everything goes through. But empirics are focused on Lasso because that's the best understood.
Thank you.
I have a quick question. So for the data splitting part, how do you compare the variation of one you use with the like cross-fitting or other like stability selection?
I see in part 3, right? Sorry, or here.
Yeah.
Oh, thank you for that question. So for Lasso, actually, you do not have to split the part. Yeah, so first let me clarify where splitting occurs. There are two stages, one where you estimate Lasso and the part where you compute the bound. If you're doing Lasso and the analysis under sparsity, under some conditions, you don't have to split the data. So in column 3, I use the full data for stage 1 and stage 2. For other machine learning techniques, you need to split your sample because there could be overfitting occurring. So if you were using random forest in column 3, you should split your data into two pieces using cross-fitting, for example. I did not experiment with that, to be honest. So column 3 is based on the full sample. But generally speaking, of course, you should be, if you're using random forest, you should do cross-fitting. But I don't have a very clear guidance on how many folds. And in that sense, I'm in line with the literature. The literature currently is open on that part.
Thanks.
Do we have any final questions for our speaker? Last chance, everybody. Well, thank you then. Let's for a wonderful talk, clear and informative and obviously very useful. So thank you very much for joining us today. Next week at the regular time, 11 a.m. Tuesday, we'll be hosting Guanting Chen from Stanford University. So thank you all for joining us today. Thank you again, Vera, and see everybody next week.